There's a powerful technique in data science called principal component analysis, or PCA. We're going to learn how to use it with some code samples. But first, what is PCA and why do we need it? Well, to answer that, we need to talk about dimensional reduction. Have you ever had a dataset with so many features that it was hard to make sense of it? Or maybe you want to build a machine learning model, but the data had too many features and it was taking too long to train. Well, one way to deal with that is to reduce the number of features or dimensions in the data. In a dataset, each feature is a characteristic or property of the data. So for example, if we have a database or data set of houses, some of the features could be the size of the house, the number of bedrooms in the house, the price, the location, that sort of thing. Now, each feature provides information that can be used to describe the houses and their characteristics. If we have a data set of 100 houses and each house has 10 features, then we can have a total of 1,000 features. That's a lot. And that can make the data hard to visualize and understand. So reducing the number of features or dimensions in a data set means removing some of the characteristics or properties of the data. And that process is called dimensionality reduction, and it has many benefits. For example, reducing the number of dimensions can make it easier to visualize the data and understand the structure. You can also make it faster and more efficient to build machine learning models. And by removing redundant or irrelevant features, dimensionality reduction can improve the performance of the models. So we finally get to principal component analysis, which is one particular technique for dimensionality reduction. PCA has many advantages. It's simple and easy to implement, and the results are easy to interpret. It's also computationally efficient and can handle large data sets. And because it's a linear method, it is fast and scalable. PCA finds a new set of features called principal components that capture the most important information in the original dataset. So let's see how we could apply PCA to our house dataset with 16 features. First, we need to load the data into a pandas data frame and standardize the features so they have a zero, mean, and unit variance. That's important because PCA is sensitive to the scale of the features. Next, we'd use the PCA class from the Scikit-learn library to fit a PCA model to the data. This class has many parameters, but the most important ones are components, which specifies the number of principal components to keep, and the widen parameter, which specifies whether to widen the data. More on all that in a bit. Now, after fitting the PCA model, we can use the transform method to project the data onto the principal components. This will return a new dataset with the same number of rows as the original dataset, but with fewer columns depending on the number of principal components we've kept around. For example, if we kept 2 principal components, the resulting dataset would have 2 columns, which we could call PC1 and PC2. These columns would contain the coordinates of each house in the new reduced dimensional space. We can then use the inverse transform method to project the data back onto the original space. This will return a dataset with the same number of rows and columns as the original dataset, but the values of the features will be slightly different. Why is that? Well, because we lost some of the information when we reduced the dimensionality of the data. We could print the explained variance ratio for each principal component in the PCA object along with some sample output. Now, this would output an array of values where each value represents the explained variance ratio of one of the principal components. It means that the first principal component explains 30% of the variance in the data, and the second principal component explains 20% of the variance in the data. The PCA class from the Scikit-learn library has many parameters, but here are the most important ones, and we've covered a few of these already. So components. This parameter specifies the number of principal components to keep, and the default value here is none, which means that all the principal components will be kept. If you want to reduce the dimensionality of the data, you should specify a value for this parameter. So for example, if you only wanted to keep 2 principal components, like in our example, you would set n-components equals 2. Whiten, this parameter specifies whether to whiten the data, and whitening is a pre-processing step that ensures that the principal components are uncorrelated and have unit variance. It's recommended to use whitening if you're going to use the principal components for modeling, but it's not necessary if you're just using them for visualization or feature extraction. The default value is false. Then there's SVD solver. This parameter specifies the algorithm to use for computing the principal components. The default value is auto, which means that the algorithm will choose the best method based on the size of the dataset. If you have a large dataset, you should probably use the randomized method, which is faster and uses less memory. If you've got a smaller dataset, you might want to use the full method, which is much more accurate, but slower. With PCA, you can take a complex dataset with many features and transform it into a simpler dataset with just a few principal components. This can make it much easier to visualize and analyze the data and help you find patterns and trends that would otherwise be hidden in the noise. So if you ever find yourself drowning in a sea of features, remember that PCA is here to help you find the most important ones and make your data more manageable.